Hello, chemistry students. This is Mr. Sheldrop, and we're going to walk through some quantum mechanical model notes. So the first thing you'll notice on this page is that I have a picture of all of the different orbitals that we would see in the model of an atom. We talked last class about the Bohr model and how that was a very simple representation of the model of an atom, which allows us to really think about the structure of the atom in a big picture sort of way. But now we want to start increasing the level of that depth. Notice that there are 4 different letters that correspond to different shapes here. S orbitals have a round shape. P orbitals are more dumbbell shaped. And as we get to D and F, they get some really funky and unique shapes. That last one in letter D is my favorite, where it's like a ring going around a dumbbell. The key part is that there is a specific number of orbitals that go along with each of these letters. So in the S sublevel, there's always just one orbital. And each orbital, which we're going to learn in a second, can only hold a maximum of 2 electrons. So if I have one that can hold 2 electrons, then my max number of electrons would be 2. And this energy level will always be present in atoms. So this is going to be present in elements on the periodic table from the first row through the 7th row, right? When we start talking about increasing level of structure, the larger that the atom gets. The p orbitals, there are 3 of them. And if each one can hold 2 electrons, 3 times 2 gets us a total of 6 electrons in the p block. Now, the p orbitals don't exist on the first energy level of the periodic table. They start on the second energy level, and we'll look at why that is based on the structure of the periodic table in just a minute. The d block, there are 5 of them, and if each one holds 2, then total you could have up to 10 d electrons in an atom per energy level. So the d block, similar to the p block, it doesn't always apply. This only starts on energy level 3 onward. So the first 2 rows of the periodic table will not have d electrons. Even the first 3 rows, we'll get to some complexities with d and f in just a minute here of how they're actually numbered. The f orbitals, there are 7, and 7 sets of 2 gives us a total of 14 electrons. Now this is only going to apply to energy levels 4 through 7. So let's go over a couple of basic definitions, and then we'll dive right into actually setting up some electron configurations. The first definition that we want to look at is the Aufbau principle. And there's a lot of terms that we're going to throw out here. We're just going to apply these rules when we write electron configurations, but it's helpful to lay them all out in advance. So this principle states that electrons will always fill the lowest energy level first. As we add subsequent electrons, it's almost like we're building outward. The electrons will then take the next lowest energy level position as you build out in complexity. Electrons' natural state is to be as close to the nucleus as possible. The Pauli exclusion principle, this gets the idea of when we're actually assigning more than one electron per each of the orbitals. When we assign each electron to an orbital, we're going to give it a specific spin. Now this is a really complex quantum mechanical idea. For our purposes, we just want to know that 2 electrons fit per orbital and that they go in opposite directions. So you can have a maximum of 2 electrons per orbital, and they're going to have opposite spins. Sometimes you'll see it like an arrow going up, an arrow going down. Sometimes you see it as like a half arrow going up and a half arrow going down. It doesn't really matter. It's just to show that there are 2 separate distinct electrons in each of the orbitals. And sometimes you'll see the orbitals drawn as like a circle, so you can label them specifically. We'll look at that on the very next page. The last one, Hund's rule, this looks at electrons, and this is kind of something that builds into the Pauli exclusion principle. We know that there are 2 electrons max per orbital. Electrons are always going to fill each of the available orbitals first before any of them actually double up. We know electrons repel each other. They're all negatively charged. So they're going to distribute themselves as evenly as possible before any of these electrons have to be in close proximity with another one. So electrons will fill each orbital with 1 electron first before any of them double up. All right, we talked about valence electrons earlier when we were talking about the Bohr model of the atom. So remember, valence electrons are electrons that are in the outermost energy level. This is going to be really important in our next unit. But we can look at the model of an atom and start labeling those valence electrons now, so that way when we get to the next unit, it all flows together. Now, this is going to be what we start to practice. We've got standard notation versus the noble gas shorthand. So when we start looking at these, we're going to write out the standard notation. This is going to be the normal way of writing it out. So this is going to be the normal long form. What we're also going to show you is how to write the noble gas shorthand, which is a much more efficient way of actually writing these. And in order to write the noble gas shorthand, you use the noble gas that's at the end of the previous row of the element that we're looking at. And the way in which we'll actually do this is that it will actually abbreviate the entire electron configuration up to that noble gas. So we'll use that notation, and we actually just write the formula for the noble gas, its atomic symbol, in brackets, and that summarizes for all of the electron configuration up to that point on the periodic table, which again I'll show you in just a minute. Electron configuration up to that point. All right. This becomes very useful when we start writing longer and longer electron configurations. Now, the last point on here is ions. I don't know if we'll have a chance to talk about this today, but we will get to this idea when an atom can gain or lose electrons. And we're losing those electrons or gaining them in that valence shell. So this idea of becoming an ion is directly linked to the number of valence electrons that the atom has. So we'll be talking about that idea, and it's either to fill or you're trying to empty the outermost shell, so you go back down to the previous full shell. All right, so let's dive in and let's actually just look at a couple of practice ones here.